Or this. So the power function, not to be confused with the exponential function, even though we use the power functions as well as the root functions in order to build this one, but it's not the same as if you just look at the graph that we have achieved at the end. It does not look like anything we've seen elsewhere. Okay, so we build it through the sequence of conventions. So these are convention number one is that repeat what is the meaning of 2 to the n. The meaning of it is that you repeat multiplication by 2 n times. Okay, well, and then what happens? Well, let me put an a there just so that we don't have to deal with 2 every single time. So suppose the sum a. So you multiply by a n times. That's the meaning a to the nth power to the x. Let's put x here. Okay. So we're talking about a function that is real variable. So the input is a real variable. Okay. So then to understand what and how it computes, we go through the sequence of expanding the x's from just a few from the first line to the next and on, until we include all of them. All real numbers will be the domain. Okay, but at this time, the line number 1 is it's an abbreviation. If x is a number 1, 2, 3, so a positive integer, then we simply multiply a by itself n times, okay, or x times. Okay. Second convention, what happens if x is equal to 0? Then a to the 0th power is equal to 1. Okay. Okay, the third convention is what if x is negative? Then we simply divide by that power. Okay. So negative power means division by that power. Okay. The fourth convention is the last one that we studied, was the rational exponents. It is the meaning of which is this. A to the power of p over q is it is a taken to the power of p and then take q root of that. Even though you can do it in the opposite order, that's fine too. So you take the q root of a and then you take it to the power p. Okay, so that's what it is. Like I said, we need power function. We need the root functions in order to build one exponential function, because all the powers should be available. So number 5 is x real, and that's still to come, but not in this course. It is explained in calculus. So what to do about those irrational numbers? What if the power, the exponent, is irrational? What it means? But at this time, it's not bad. Even if we only got to this point, we were able to fill all of these points, all the gaps. There are literally no gaps here. So the rational numbers are so close to each other that they leave no gaps. What do they leave? They leave cuts. So the irrational numbers never touch each other, which means that there is always a cut between them. Because there is between two irrational numbers, there is one irrational number, which means that no two rational numbers are actually connected to each other. That is why it is not a curve, even though it might look like one. It is because there are no gaps. No gaps, but there are cuts. So it's like a rope, and if it has a cut in it, it might look intact. But if you pull it apart, if you pull it to the sides, it will be broken into two. Okay, so that's what I'm saying. There are all those cuts throughout. So x equal to pi, x equal to square root of 2. All of these are missing numbers, but we will just ignore that and we'll just accept it, as an assumption. So a to the x is defined for all real x. So no cuts, no gaps. Okay, so the graph then we see on the right is exactly what it would look like. In fact, there are two main cases. Case number one is a larger than 1, which is like this one, 2 to the x. So it looks like this, passing through 1 and then increasing, well, probably faster, and that is the reason for using the expression exponential growth. Okay. So it is a to the x, y equal a to the x with a larger than 1, 2, 3, or whatever. And then case number 2, a less than 1, but still positive. If in any doubt, you just remember where we started. We started with repeated multiplication, which means that's why we have growth. Because if a is larger than 1, then you keep multiplying by a, it will be growing. So a times a times a, you have growth. And it is a fast growth. Like you multiply by 2 every time, so certainly it grows faster. When a is less than 1, you multiply by, so once again, these could be 2's. What if you multiply by 1/2 and you keep multiplying? What?
It gets smaller.
It gets smaller. It gets smaller, and also just as a dramatic way, like this. So it also passes through 1, and it's called exponential decay. A less than 1. So examples, remember once again exponential growth when over populations. If the growth rate is proportional to the population, then you will be multiplying by that number on and on. Compounded interest, multiply by that number on and on. And exponential decay, if then when the death rate is higher than the birth rate in exactly about the same way, it will be declining by, you will be multiplying by the same number on and on. Say 0.95, if you lose 5% of the population every year, then you multiply by 0.95 on, and it will eventually get to 0, inevitably. Okay, so in some decays and cooling too. So population and cooling. So in fact, I might illustrate this like this. So if this is room temperature, then you might bring you might bring a cup of coffee in it, and it will be cooling towards that value of the room temperature. It will never pass it, and with time it will be virtually indistinguishable from the room temperature. What if I bring a can of soda instead of coffee? It gets warmer. Yeah, so can you describe the picture? Yeah, so but it is like the same graph only upside down, right? So it will have the same growth. Well, not exactly, but this is roughly what it would look like. So roughly the same picture, graph only upside down. It is probably, I would say it's probably steeper because the coffee, especially in a cup, it will be cooling slower than the soda is warming up if it is in a can. So those degrees of growth, so this one is faster, I think, are determined by the value of A. So whenever A is larger, so such as like this is 2x, and this is 3x, and it grows faster. Okay, similarly on the decay end, we have also similar behavior. So if this is, say, 0.1 x, then 0.2x will be declining not as fast like this. 0.2x. Okay, so there is this whole spectrum of exponential functions, and they all pass through the same point. So they all have the y-intercept at 1. But other than that, they either decrease or increase based on whether a is larger than 1 or less than 1. And then if within those two classes you have also faster growth or slower growth, and so you can actually have let me have the whole picture here. All the exponential functions at once, so they all pass through this point, and then you have a growth like this with decline here, and then you have a slower growth like this, and then there's an extreme case of a constant function that separates increasing from decreasing functions, and here I have a decrease like this, and one more. More color. Okay, so these are once again just 4 examples of exponential functions. This happens to be constant. This is, say, maybe 3 to x, 2 to x, and this is once again 1/3, maybe 0.1 x, and the other one 0.2x. Okay, so once you look at them, you already might notice some patterns in addition to increasing, decreasing behavior, and that is, well, let me change this. Well, let's look at the green one, the two green ones, the light green and dark green. Do you see any relation between the two graphs? So this one and that one. They're mirrors, right. So y equal 2 to the x is the mirror image. Or rather, what is its mirror image? So what's the other graph? How do we create a mirror image horizontally? So if we start with y equal 2x, what's the other one? So the light color is 2 to the x, and what's the dark green? Remember how we make a mirror image? Well, right, that's the answer, but how would we do it? We do it by replacing x with the horizontal flip. X replaced with negative x. Negative x. Negative x, yes. So x, this is, if this is 1, the opposite is negative 1. That's the flip, right? So x becomes negative x, right? And so the function of y equal 2x, it becomes y equal to negative x. And then to confirm the algebra is what just was brought up a minute ago. It's the same as 1 over 2 to the x, or the same as 1 over 2 to the x. Okay, so those properties we talked about recently, about the properties of algebraic properties of the exponential function, are all up here over there. And turns out that replacing x with negative x, the flip of our graph does produce a new or old exponential function. So in other words, this one is base 2, exponential function base 2, and this one base 1/2. And so one of them was larger than 1, and it was increasing. And once you flipped it, it became decreasing. And the base is less than 1, right? So 2 larger than 1, and this one is less than 1. So every then increasing exponential function can be flipped horizontally, producing a decreasing exponential function. And what happens to the base? It becomes its reciprocal. So if this is y equal ax, then it's symmetrically will be, what is it, y equal 1 over ax. But both of our exponential functions, we literally flip the base. So the base was a, and we took its reciprocal 1 over a, and it's a new exponential function. Okay, so that's one symmetry that we observe if we look at all exponential functions at once. There is a symmetry of with respect to the y-axis. So the horizontal flip will produce more and more exponential functions. From exponential growth is converted to exponential decay in that manner. Like this is the flip. Okay, and but that's not it. There is also another thing to discover about the patterns or connections between the different exponential functions. So what if, let's stretch y equal 2x horizontally. Well, let's shrink it. We shrink y equal 2x horizontally by a factor of 3. What's its graph? When we shrink horizontally, what happens to x? Remember, every time we do the substitution, so just like over there in the previous example, we replace x with negative x. When we do horizontal shrinking, we replace x with... No, what? No, not minus, just 3x. Yeah, just 3x, 3x. Okay, so horizontal shrinking. Remember, whenever it is horizontal, to shrink you multiply, and to stretch you divide. Okay, so we are shrinking horizontally, which makes it taller, like this. Okay, so that's the second one. But you already can see that it has a similar graph. It has a similar graph. It looks like another exponential function. At least it looks like it, like one, right? It has the same passing point. Remember, it is shrink horizontal, which means that the y-intercept doesn't change. It only becomes slimmer on the right, and on the left, you can see what has happened is when we push it towards the y-axis, it kind of still becomes steeper. It is steeper in this area. It is still steeper, while elsewhere it remains horizontal, kind of. Okay, so it looks like another exponential function. We can confirm it if we just remember the algebra. So it is also an exponential function. What is a? Two to 3x is equal to a to the x. I want to identify this new curve that looks like an exponential function. I want to confirm that it is an exponential function. I just need to find the base. What's the base of the new exponential function? Two. What? No. We need to solve this. So find a from this. 2 to 3x is equal to a to the x, and then we need to find a. Can you transform this one, 2 to 3x, using one of the properties? Yeah? 8, that's right. 2 cubed to the x, that's one of the properties. Remember, it is actually new property number 3, that's the way we use it. So then it turns out to be indeed a to the x power. Okay, so indeed, that's my a. A is equal to 8. Y equal 8x. So it's also an exponential function, just the base is different. So horizontal flipping, the previous example, this one, showed that horizontal flipping produces of an exponential function produces another exponential function. Now, horizontal shrinking or stretching of an exponential function also produces an exponential function, just a different base. It is very similar to parabolas. Remember, there is only one parabola, and then from one single parabola, y equals x squared, you can produce every single parabola that you can think of by stretching, shrinking, flipping, and shifting. Okay, so we have fewer operations here, but the idea is still the same. So we can cover all possible exponential function in this manner, right? So either if you have only one exponential function, say 2 to the x, you can start with that one, and then you can acquire every other exponential function in this manner, either flipping to get the exponential decay, or you stretching and shrinking vertically, horizontally, in order to get different bases as well. So it is very similar to the situation with the quadratic functions. So all it takes is some operations, some transformations of the plane to get a new any exponential function you can think of. You can get it in this manner. Just like well, to refresh your memory, so say 3x squared is equal to 9x squared, right? So you take your function x, replace x with 3x, and you get a new quadratic function, right? Or you can flip it vertically and get an upside-down parabola. So it's a very similar story, and that's a good news because then, as we discovered with the parabolas, you need only one parabola, and then you get all the rest of the parabolas through transformations. Okay. Similarly, you need only one exponential function to get all of them. Okay. The only question remains, and that's an interesting question, which one to pick. If anybody knows the answer, which of the exponential function would you pick as one representative? Well, it's virtually impossible to guess unless you know. So it's we pick or in calculus we'll pick one that crosses the the y-axis at 45 degrees. This one. So it means that you cut all exponential functions in half. Those that are steep, and those that are kind of shallow. So 45 degrees is like higher than 45 degrees is steep, lower than it is they're kind of shallow. So or if you like, its slope is equal to 1. Okay, so we pick this one as the best, the only exponential function that we care about, and the base is e, the natural base. So every calculator has that button, that e. So y equal e to the x is the natural base exponential function, and it is among all of these. In no way it is better, with this exception. That's an exceptional property, that it crosses the y-axis at 45 degrees, and that is, roughly speaking, the reason why we pick it as a representative, as the function, as the exponential function for which to build every single one of them. Okay, so that's a little bit of algebra. The properties of the exponents that I have listed here somewhere that we're going to need. So these are the properties, but at this point the conventions are important. And another important thing is certain properties that we derive from simply examining the graph. So all the graphs. So these are all the exponential functions are here in this picture. What is so good about them? They are all one-to-one. So the exponential function, base a, greater than 0 but not equal to 1 naturally, is 1-to-1. We certainly have noticed that from by simply examining the picture. What else we see here? Domain is as planned, negative infinity plus infinity. The range, so fact number 1, 2, and 3. What's the range? Looking at the picture, what's the range? 0 to infinity, excluding 0. Okay, so certainly you can guess why we care about one-to-one. It's almost every time it comes up, it means that we'll be talking about the inverse. So it is invertible. It is invertible, and you can already say on fact number 2 and number 3, you can tell what that new function will look like. It will have, this will be its range, the inverse, and this will be its domain. So domain, as you can see, of the inverse will not be everything. Okay, it will be limited to 0 infinity. It's called the logarithm. Base A. So each exponential function has a base, right? And then its inverse is called the logarithm that base. Okay. So let me quickly do the flip that produces the graph of the new function. Okay, so let me take the graph. Okay, so this is roughly my graph of my this is the graph of my exponential function. Okay, a greater than 0 here, a greater than 1. Okay, so let's flip it. So I'm flipping it. Okay, so I'm gonna remember how we find the inverse. There is a rotation or 90 degrees first, and then we flip it vertically. Okay. One more time. Okay.
That's how you find the inverse.
Yeah, we're finding the inverse, right? So if this was, the original one was e to the x, e to the x, a to the x, this one, and this one is a to the log base a. Log base a of x, if this is x. Okay, so you can see the domain, right? So the whatever was the range has become the domain. So this one, it was the range. Now it is the domain, and conversely. Okay, so the inverse of the exponential decay function looks slightly different. So I'm going to do that just in case. So I have my other x's. Okay, so my exponential decay function looks like this. A less than 1. It's still ax, but it's less than 1. And then once again, I carry out the flip. Rotate 90 degrees, and then flip vertically. Okay? So it's pretty much the same as the last one, only upside down. So this one is log, it's still log base AX. The names are the same, it just happens to have that quite a bit different behavior. But the domain is still the same, and the range is still the same. So 1 if in the first row both functions are increasing, so the inverse of increasing function is still increasing. In the second is decreasing, and once again it is decreasing. Okay, so that way we have all the, in one swoop, we got all the inverses, all the logarithm at once. So that's the easiest way to get started with a logarithm is the inverse of the exponential function. Which one? Every one. Okay, so every exponential function has the inverse, they all one-to-one, so each one of them has the inverse, and at once you have all the logarithms available. But we mostly look at the one on the right as a representative, because they are once again all very similar. You can compare in the second row, you can compare the first and the second. It's just a vertical flip, just like the first two in the first row. There it is horizontal flip. In the second, in the first column, the 2 is just a horizontal flip. We just talked about that. But in the second column, it is a vertical flip now, right? So, but it's the shape is exactly the same. So we are not worried about that. Okay, so let me summarize what I have here. So everything is the same. So the logarithm function base A, once again greater than 0 but not equal to 1, A is 1-to-1, and the domain is 0 infinity, and range is negative infinity infinity. So once again the graph is this. So it slows down, it's increased, but it never stops. So that's why the range is everything. It keeps going. But here, as you can see, it behaves in a manner similar to those rational functions. Remember, they had those vertical asymptotes. We call vertical asymptotes those that are where the vertical line which the graph cannot cross. And that's why it starts to climb. In this particular case, it starts to climb down. But it matches, that behavior matches the behavior of the exponential function. As you can see, the behavior over here matches the behavior over there because it's flipped. Hold on a second. And over there. Okay, so if we have horizontal asymptote on the left, then on the right we have a vertical asymptote because everything is flipped. Every x becomes y. Everything that it was horizontal becomes vertical and vice versa. Okay, so once again, this is the kind of holistic view of a bunch of functions that you see at once, and they're described in this fairly straightforward manner. Okay, we also know that the exponential functions are represented by pretty much one single picture, and from that picture we derived all the rest of them like this. Okay, now we flipped everything about the diagonal, as we always do. Okay, and then we got the inverse, and then all of those facts still applicable. Not only this short description is there, we derive very quickly, but also we have all of those, all of the ability to derive the rest of the logarithms from one single logarithm, and that is incidentally the match is LNX. That's what it stands for. A special name for the function is natural logarithm, lnx. So, and every other logarithm can be derived from it through simple stretching or flipping. Okay, so it's just can go faster, it can go slower, but or you can flip it upside down, but it's the shape is virtually identical. That is why it pays just concentrate on one of them and just not worry about how you switch between them. But what the challenge of the logarithm is not this quick workout that we got them all at once, but rather the algebra, and we have to go back to the algebra in order to in order to really complete really complete and understand the logarithm. So if we have the three main properties of the exponential function, these are the ones. List them any time. Yeah. So I guess let me list them, and then we'll find the corresponding properties of the logarithm. So back to algebra, and we start with the logarithms. We start with the exponential functions, and so the properties are ax, ay is equal to ax plus y. Property number one. Property number two, ax bx is equal to abx. Property number two. Once again, all coming from repeated multiplications. Repeated multiplication. So the first row, you multiply a by itself x times, then you multiply by itself y times. Altogether, you multiply by x plus y times. Okay. And the third one is ax y is equal to ax times y. Once again, counting. You multiply x by itself, and then you do it y times. Altogether, you end up with a table of x by y table of a's, and then how many a's do you have here? X times y. So this is the table over there I was talking about. So it's entirely about counting. And it matches, by the way, that's what we did previously, matches what we know about addition. So from addition, repeated addition gives us multiplication. Repeated multiplication gives us power, an exponent. Okay, but these properties are simply to be remembered, and but just it's easy to remember if you know where they come from, and that's where they come from counting. Okay, now the challenge becomes now what are the corresponding properties of the logarithm? Okay, so there will be also as many algebraic properties of logarithms, plus there will be also conventions that we will have to review. But we'll start with this. So just the simple properties, and unfortunately we cannot really go with counting of how many times things appear. That's where these formulas come from. But logarithm, we have to simply do some substitution. So derive by substitution. Okay? So we're going to derive them, but I think we probably should talk about, maybe I'm just jumping forward too fast. Let's talk more about the logarithm on a more basic level before we get to the rules. So y equal a to the x, and x equal log base a y are inverses of each other. What does it mean exactly? Remember, you substitute one into the other, one way or the other, the two ways to do it, you end up with where you started. Okay, so you apply exponential function, then logarithm, or first logarithm, then exponential function, you end up with the same. So it means the following. So if I start with ax, and then I substitute x in here, I have a log base a at y, and it is equal to y. So there will be two substitutions. So either I substitute logarithm to the exponential function, and I end up with the same thing. A taken to the logarithm base a gives me y, and number two, I do the opposite. I substitute the exponential function into the logarithm. So it will be log base a of a to the x, and it's equal to x. So this is the cancellation. Cancellation, or undoing the effect of the other function, the idea of the inverse. That's what it means. It just now it is just one specific example of how it works out. And it really explains what the logarithm is. So if you understand inverses and understand exponential functions, then you understand logarithms. It just takes a bit of time to get used to it, and that's what we're going to do it right now. Okay, so this cancellation. Let's take a few more specific examples. So, for example, 8 is equal to 2 cubed. Okay, it can be rewritten in terms of the logarithm as follows. Log base 2 of 8 is equal to 3. Okay, so this is the base. 2 is the base. As you can see, it's whatever is at the bottom is either on the left exponential function, whatever at the bottom is the base, or the one that is below the subscript in the logarithm, that is the base. Okay, and then we have x and y. This is x, and it reappears here, and then we have y. And this is y. So it is the same statement. What is important to understand is that what I have written here is the same thing. What's on the left and what's on the right, these two statements are identical, pretty much. It's just different point of view. So either you go from x to y or go from y to x. That's what's happening on the left. And on the right, it is still the relation between these two numbers is the same. So you on the left, you go from x to y, from 3 to 8. On the right, you go from 8 to 3. Okay, so you could always put it in words, which helps sometimes. So I could take the statement on the left and interpret it and attach it to the statement on the right. So what I'm seeing here is 2 taken to the third power is 8. Okay, so that is literally what's happening on the left, but you should be able to see it on the right as well. So that is in the reverse, that is the meaning of the logarithm. Log base a of y is to what power I raise to get x. No, hold on 1 second. To what power do I raise a to get what? Okay. So that's if the formulas don't work for you sometimes, it's better to have also as an extra way to look at it is the verbal description. So once again, the logarithm is to what power do I have to raise x to get y. Once again, it's in the backward direction. Whatever the y is on the inside, how do I get that y as a power of the base? And the answer is, and if you compute it, you have the answer. So once again, I can rewrite it as here. 3 is equal to log base 2 of 8. To what power do I raise 2 to get 8? And the answer is 3. Or 25 is equal to log base, I'm sorry, that's not what I meant. 2 is equal to log base 5 of 25. To what power do I raise 5 to get 25? The answer is 2. Okay. Okay, one more. Well, we need to do a few of these. Log base 10 of 100, or 1,000. The answer is 3, right? To what power do I raise 10 to get 1,000? The answer is 3. To what power do I get to raise 10 to get 0.1. Well, you can log. You can just go through some algebra. It is 1/10, right? Literally 1/10. How else can you write 1/10? What? No, I don't want to go backwards. 1/10. It is a certain power of 10. What we just talked about. Division is the same as negative power. It's negative first power. So then the answer is -1, right? So that's roughly how it works out. You just have to represent that number, if you can, in the form of a power of the base. So that's what I did. This computation was the way we compute logarithms whenever we can, and we convert the argument, that 0.1, into a power of the base. So this is the argument or input. And this is a power of the base. So if you can do that through some manipulations, you will end up with the answer. Your answer will be visible right there. Okay, so one more. Say log base 4 of 2. Log base 4 of 2. Once again, try to represent 2 as a power of 4. 2 as a power of 4. What's the relation between 2 and 4? No, yes. It is square. 2 is the square root of 4, right? Okay, so and now if I want to represent square root of 4 as a power, what is it? It will be 1/2. So it is 4 to the power of 1/2, which means that is the answer. Okay, so this is irrelevant. That part that disappears. Only the power it remains, and that's the answer. So just like here and elsewhere, logarithm and the exponential function of the same base cancel each other, and you have your answer. Okay? Okay, so see you next time.